Alright, so we're going to pick it up today. We're still on 5.3, which is R E I. Dang it. Riemann. Alright, 1M. Sums. With that 1M. Okay? Alright, we're going to continue. Now we're going to talk about the definite integral. But now we're going to talk about the definite integral as an area of a region. Yes, sir.
Have we done 5.3 the beginning of it as the summation stuff that we did?
Mm-hmm.
So we're just continuing.
Yes. Okay. All right. Let's talk about it. In other words, you found out through that video that in order to integrate, you must be continuous. So if it is continuous, it is integratable, right? So if f is continuous, but now I'm going to add something, and non-negative on a closed interval from a to b, then the area of the region bounded by f of x, whatever function you have, the x-axis, and the vertical lines x equals a and x equals b. Oop. Is found the following way. Area equals to the definite integral from a to b of f of x dx. Cool? Which literally means we can make the connection. This is part of the formula, but it just wants you to make the connection. That's the same thing as saying the limit as the norm approaches 0 of the summation from 0 to n of f of c's of I times delta xi. Cool? That's all it's saying. It's making the connection of what we've been doing. That's what we've been doing. The limit as the norm approaches 0, which is another way of saying the limit as the number of rectangles approaches infinity of an area under a curve of the summation of some function times the width of the rectangles. In other words, the length times width. It's the same thing as saying a definite integral from a to b of that function in terms of d of x, in terms of x. Cool? All right. So let's try an example. Let's say you have the definite integral from 2 to 4 of 3x squared dx. Cool? Did we? It was? Oh, but we did this problem through the limit process, didn't we? Right? So you already know the answer to this problem. What's the answer? It's going to be 56. Okay? However, there's a catch to this because I know some of you guys already know how to integrate this and find the answer just by, because that's called the fundamental theorem of calculus. That's what we're going to hopefully get here later on the video. So, for now, I'm going to assume you still don't know the fundamental theorem of calculus. Right? However, you know that this is the same thing as this limit. Agreed? How can we rewrite this in terms of a limit? Well, we know that the limit as the norm approaches 0 of, well, wait a second, we have I starting at 1, right? Sorry. It goes to n. Agreed? And we need to do f of c of I times delta x. Well, how are you going to find delta x? Well, isn't this the same thing as telling you find the area of 3x squared from the interval from 2 to 4? 4 minus 2 over n, because I'm not telling you a number of rectangles, right? It could be infinitely many. So delta x is going to equal to 2n, right? You guys with me? Now, in order for me to continue this problem, I need to find c of I. Agreed? How are you going to find that c of I? Well, I recommend that you use the right endpoints, and we just talked about this formula. It's a, what's your a value? 2 plus what? Well, we need delta x. Our delta x 2n, but I need to multiply that by what? Just I? Very good. You guys remember that formula? So therefore, we can say that c of I is equal to 2 plus 2i over n. Agreed? You guys with me? Yeah. C sub I. No, it's just it's because of the index being I. That's all. Okay. So now, we can then say that this becomes the limit as the norm approaches 0 of the summation of I from 1 to n of, well, we know the function of f, don't we? So it's going to be 3 times what? 2 plus 2i over n squared. Agreed? Times what? Times delta x, which is 2n. Agreed? Alright. Just because I need to make sure that you can do this, because this will be on your quiz, you've already know how to do this. We did this last class. Finish the problem up. Use your summation formulas. This is a good practice before your take-home quiz. Use your summation formulas. Expand this out. Simplify it. Get rid of the summation so that you only have a limit. Now, the only thing that I'm going to help you with is remember that this means what? It's another way of saying the limit as what? N approaches infinity. What does the n represent? The rectangles. Agreed? The width of the rectangle. So in other words, how many rectangles you have. Agreed? This is the same thing as saying this. So just make that transition. Switch from here to here so that you can solve. Because you will not, after you get rid of the summation, do you guys agree that you're going to be only in terms of n now? In terms of n. Cool? Alright, go for it. If you think about this problem, this is technically saying that f of x is 6. And that you're finding the area of that function between -2 and 3. You guys agree on that? Like all I'm doing is translating this problem into a function and the closed interval. Well, if you think about it graphically, f of x equals to 6 is just a horizontal line at 6. I'm going to pretend this is 2, 4, 6. So we have a horizontal line here. And I want the area between -2 and 3. So if this is -2 and this is 3, I'm looking for this area. And rather than doing any calculus, you can find the area of this very easily with geometric formulas. This is a rectangle. Area equals length times width. So from -2 to 3, that's a total of 5. And what's your height? So what's the area under the curve? 30 units squared. So in other words, I'm going to be honest, you can save a lot of time, but to be completely honest, you can integrate this very easily. You can recognize that if you just have a constant, you're going to have a rectangle, y'all. Okay? What if you have something like this? Definite integral from 0 to 5, 2x dx. Well, doesn't this essentially say that you have f of x being 2x and you are going on a closed interval from 0 to 5? Well, graphically, here's what we know. 2x is just going to be a line with a slope of 2. You guys agree? So if we're starting at 0, here's 1, here's 2, 3, 4, 5. And I plug in 0, that's 0. 1 times 2 is 2, so let's go by 2's here. 2 times 2 is 3 times 2, 4 times 2, 5 times 2. Agreed? So then you have a triangle, right? We're looking for the area under the curve. So remember, this is technically still going on forever, but we're only interested between 0 and 5. So the area becomes 1/2 times the base. Your base is 5, and your height is 10. So 25 units squared. Definite integral between 1 to 4 of negative x plus 7 dx. Well, some of you may have made the observation that this, first of all, we had a constant, so that was a rectangle. Now we have a line, so it was a triangle, but this is also a line, agreed? So maybe it's a triangle. However, you have to be careful, because this time we're not starting at 0, we're starting at 1, so it might not end up being a triangle. It could be something else. Okay. Negative x plus 7 is a line with a slope of -1, starting at 7. So up here, and then you're just going by ones, right? Keeps going in that direction, keeps going in that direction. But I'm only interested between 1 and 4, right? So if this is 1, 2, 3, 4, this is what I'm interested on, and I only need the area of that. So I know it looks like a triangle at first, but now that I apply the restrictions, it's no longer a triangle, it's a trapezoid. How do you find the area of a trapezoid? So 1/2 base 1 plus base 2 times the height, right? Area equals 1/2. Base 1 is 1, 2, 3, plus base 2 is 6, and the height is down here, right? Area equals 1/2 times 27, so 27 halves units squares. Lastly, the last geometric shape I want to show you is the following. And this one's a little tougher to see, but not really. Because technically your equation here is f of x equals to the square root of 9 minus x squared. Agreed? F of x is another way of saying y. If I square both sides, I get y squared equals to 9 minus x squared. This is a circle. X squared plus y squared equals to 9. So this is a circle with a center of and a radius of 3. So technically this looks like the following. 1, 2, 3, 1, 2, 3, 1, 2, 3. However, remember how I said that it can be non-negative? We only care about the positive part of this. So area is going to be what? Well, it's half of a circle, so it's going to be pi r squared divided by 2, because I only care about half of it. Yes, sir. Good. can make it negative 3
Yeah,
to make my life easier. Sure, just to move on, I'm gonna be honest. Okay, let's make this negative 3 just to move on. That way it will be the entire half of the circle, cool? Um, so radius is 3. 3 squared is 9. So 9 pi over 2 units squared. Cool. If we wanted from negative 1 to 3, that means we would be interested from here to there. And it just makes the process a little bit more, it just takes a few more steps, but you can still arrive there. Okay? To be completely honest, this, once you learn the fundamental theorem of calculus, it's not really like on the top of the things you need to remember. This would be like really at the bottom of things. Okay? Alright, let's get to what I really care about, which is about to be the fundamental theorem. When we get there, I need to make sure that you know some properties of definite integrals. So let's talk about them. Cool? Alright, so properties of definite integrals. We have two very special definite integrals. So let's talk about those first. So these are just two special definite integrals. You're about to find out. And it's very common sense in my opinion. Is defined at x equals a, then the integral from a to a of f of x dx is equal to Remember how the definite integral helps to find area? If you're going from a to a, are you moving at all? So what's your width? So can you have an area? No. Okay? So don't waste your time, don't get tricked, because you could have a very complicated thing to integrate, but if it's going from the a to a, don't even bother integrating, it's 0. Okay? If f is integrable on a closed interval from a to b, then, and this one's a kind of an important one, if you have the integral from b to a, look at the way I wrote it this time, from b to a of f of x dx. In other words, if this number is bigger than the top number, that really doesn't make sense too much, right? It's kind of like, wait, what? We're starting from the right instead of the left. We can rewrite this instead as the negative integral from a to b of f of x dx. So what did I do? I just made it into something that we know, but in order to make that switch, it makes it a negative. Okay? There are proofs on this. If you'd like to look them up, you're more than welcome to do so. So let's just try an example. So let's say I give you the following. The integral from 2 to 0 of negative x squared plus 6 dx. And I'm going to go ahead and give you the answer. It's negative 28 over 3. Using properties, I want you to find the integral from 0 to 2 of that same function. So what's the answer? What is it? 28 over 3. You don't have to do any work. All you have to do is have a negative out here. Negative times a negative makes it a positive. Cool? Alright, here's another property. This is called the additive property of integration. If f is integrable on 3 closed intervals. Interesting. Which are determined by A, B, and C. Then, so if f is integrable on 3 closed intervals determined by A, B, and C, then the integral from A to B of f of x dx is equal to the integral from A to C of f of x dx plus the integral from C to B of f of x dx. And that makes no sense at all to me, so I need to see something visually. Okay, so I'm going to show you what this looks like. It's, well, there's two scenarios, so we got to talk about both. What if C is smaller than B, but what if C is bigger than B? Okay, so first let's talk about with something. Let's kind of give us a sketch so we kind of know what this means. So let's pretend you have a graph that looks like that. And let's say that you have this being A. Let's say that this right here is B. And then let's say that this is C. So in other words, C happens to be on the closed interval between A and B. You guys with me? So if I wanted to find the area of this, I could say from A to B, I can say the following. I can find the area from here to here, which is from A to C of f of x dx, right? And then I can find the area from here to here. Agreed? So plus from C to B. Do you guys see now how the formula came about? We'll talk about that coming up. So hold on. Okay. A good example would be when we're using absolute value functions. Okay. Alright. Do you guys understand how for this it makes totally sense what we did there? Alright. Do you guys have the sketch down? Alright. What if C is bigger? So what if instead I have something like this? I'm going to pretend that we have the same graph, so something similar to that. I'm going to say that this time this is A. I'm going to say that this time this is B. And I'm going to say that this time this is C. What's up?
Why don't you just do like A to B and then B to C? But are we going from A to B or A to C?
Well, I'm just showing you how the formula works. That's all. I'm going to be honest with you. I don't see why I would go from A to C, because we're just interested in A to B, right? That was what the formula said, right? But let's just apply the formula to a scenario like this. It says, for this, that we are going from A to B of f of x dx, right? Well, that will be the same thing as saying the integral from A to C of f of x dx, but at that moment you're like, well, wait a second. The formula says then, and then I have to do plus from C to B, right? Of f of x dx, right? That's what the formula says, correct? All I did was rewrite the formula one more time. You guys with me? But you're like, wait a second. I'm only interested from A to B. And A to B is this part right here. Right? So if I find the integral from A to C, I'm finding everything. So therefore, I'm not interested on this. So what do you have to do? Minus. But it's not from C to B. I just made a mistake. It's from B to C. Understood? Let me, where's my thing? Sorry, I wrote this wrong. Because remember how we always start on the left? So it's from B to C. Good catch. Let me show you some examples. Okay. Ready? Alright, let's start just using some of these properties. So examples. Solve the following. And this shouldn't take you that long. What is that equal to? Cool. Solve the following. If you know the fundamental theorem of calculus, you cannot use it yet. You can use anything we've learned up to right now, but not the fundamental theorem of calculus. I need you to solve that following integrand. You have two options. You can use the limit process, or I'm starting to think this might be one of those geometric figures. Maybe if I can sketch it out, I can see it. Okay, so up to now, you still don't know the fundamental theorem of calculus. So try this one out without the fundamental theorem of calculus. Here's the answer. Moving on. Alright, so if f and g are integrable on a closed interval from a to b, and k is a constant, then the function kf and f plus g are integrable on a closed interval from a to b. And we know two things. Number one, the integral from a to b dx can be rewritten as k times the integral from a to b of f of x dx. In other words, what is it telling you that you can do? If you have a constant in front of your function, you can just take it out to make your life easier. You don't have to, but you can. Cool? Well, and these two things are true. Right? Number two is that if you have an integral from a to b of f of x plus or minus g of x, obviously this is dx, that's the same thing of saying the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So in other words, what is it telling you that you can do? Split up. Remember how with a limit we were able to split up a polynomial into a whole bunch of terms and just find the limit individually? It's the exact same thing for integration. Okay, if you have two different functions, you can break them up if you need to. Okay? We'll try one example and we'll finally get to the fundamental theorem of calculus. Example number 1. Integrate from 1 to 4 of negative x squared plus 6x plus 8 dx. Again, you still don't know the fundamental theorem of calculus, so you cannot use the fundamental theorem of calculus. But now I introduce you to a couple of more properties that now can make your life easier. I would not try to graph this. I would try to use the properties that I just showed. I could actually use both of the properties that I just showed you. What would you try to do first? Yes. Can I break it into 3 separate integrals? So from 1 to 4 of negative x squared dx plus integral from 1 to 4 of 6x dx plus integral from 1 to 4 of 8 dx. Agreed? Okay. Now, we know for sure from here that this is a rectangle, right? That's a rectangle. So the area of that is going to be, this is the height, 4 minus 1 is 3, 8 times 3 is 24. So this becomes 24. Agreed? If you need to draw the picture, you're welcome to draw it. Now, for time's sake, I'm going to tell you the rest of this so that we don't have to sketch this out. But this right here, when you draw it out, this is going to be a line, 6x. So you start at 0, 0 with a slope of 6, right? But because you're not starting at 0, you're going from 1 to 4, this is going to be a trapezoid. And when you sketch it out and try to come up with the area, you're going to get that the area is 45. Finally, there's not a way to use any of the geometric shapes that we have, so you would have to use, as of right now, a Riemann sum. Have to do the limit process, etc., 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 and eventually you're going to find out that that becomes negative 21. What's up? Alright, Riemann. That guy must hate me. Alright, then you just add them up and you get 48 units squared. Cool? Finally, we have reached the moment that all of you have been waiting for, and I've been waiting for, because honestly, at this point, I'm tired of the limit process. I'm tired of using geometric shapes. We can now do these problems in less than 30 seconds. You ready? Let's do this. 5.4. We made it.
How many sections?
Before the test, we're going to go all the way to 5.6. Nearby, yes. 5.4. The fundamental theorem of calculus. Sometimes for short, I use FTC. Okay? Just for short, because I obviously a great writer, obviously. Okay. All right. Here's what I need you to do first. I'm gonna ask you to go get a book, and I need you to read a page before we get started. So if you're watching the video, log into the textbook webpage, and I need you to read page 313. So go ahead and grab your books, and I need you to just read that page. All right. The fundamental theorem of calculus. Here's what it says. If a function f is continuous on a closed interval from a to b, and at this point you're like, I am tired of writing the same thing over and over again, and capital F is an antiderivative of lowercase f on the closed interval from a to b, then the following is true, and this should make you very happy. The integral from a to b of lowercase f of x dx equals to the capital F of b minus capital F of a. It's just differentiating. That means that f of x is what you had your integration of. Capital F is after you integrate. Okay? In other words, if you want to think about position, velocity, etc., this will be your velocity, and if you take the integration, it'll give you your position. If you want to take your acceleration, then this will be your acceleration, and then you'll find it. Cool? All right, in other words, this is telling you something very, very awesome, in my opinion, that you can find the area of anything by integrating. Once you get your results, if you can evaluate at the top value and subtract the bottom value, you got the area. No more limits. Cool? Wait, what? What does that have to do? Wait, what?
Because if you go to like geometry, then you're going to be using this instead of like the actual.
Oh, I see what you're saying. So yes, please, if you go help geometry kids, don't integrate, please. Go back to regular geometric formulas. All right, so here's what you know. Now you have a way to evaluate a definite integral without using limits. No, thanks to limit, everything exists. I mean, not everything, but calculus exists thanks to the limits, okay? So, in other words, I'm not telling you to completely forget about the limit process, but we don't really need the limit process anymore, right? Because now we have this faster way of doing things. Okay. In order to work this type of problems, there needs to be a certain type of notation, and they're going to be looking for this on your AP exam, so you have to use this notation. So you're going to use the following notation. Here's what it's going to say. So you're going to have an integral from a to b of some function in terms of x. When you integrate, then you're going to get an answer, so it's capital F of x, right? Plus some constant, right? You always get a constant when you integrate, correct? Well, what you're going to show the reader, whoever's grading, is that you're going to take that and that you are going to evaluate it from A to B. So you have to show this step right here. Then, if we can simplify this, you don't have to show this, but this is what it happens, right? So you need to take this and evaluate it at B. So then you have F of B plus C, right? Minus, you're going to take this and evaluate it at A. F of A plus C. Agreed? What's going to happen? And that's why, if you notice on the definition that I gave you, it is actually not necessary for you to, when you integrate with definite integrals, to have a constant. It's going to cancel away. Indefinite integrals, you must have the constant because we're talking about a family of functions. And you can then make a slope field. Agreed? So now you know that you don't necessarily have to have the constant of integration once you integrate a definite integral. Okay? Alright, let's do this. Examples. Evaluate the following. Problem number 1, and I'll let you try this one on your own. So I'll write down 2 of them. From 1 to 4 of 3 square root of x dx. And the second one I would like you to try is from 1 to 2 of the square root, not the square root of x squared minus 3 dx. Use the fundamental theorem of calculus to evaluate, please. It's going to be a terrible video. Alright, we tried this one. I'm sure you can handle that one on your own, but let's talk about this problem. So if you're integrating something with the absolute value, that means that if we go back to using limits or geometric shapes, you're finding the area under this curve. Well, if we graph the absolute value of 2x minus 1, well, what is that going to look like? Well, you know that the parent function of an absolute value has a very sharp turn. And we've talked about sharp turns not being able to differentiate them. Agreed? We talked about that. Okay. Now, for time's sake, this is going to look something like this. Let's say that this is 1, 2, 3. So at 1/2, you're going to have a sharp turn there. And it's going to look like something similar to this. This is not an exact sketch, so just something like that. Okay? This is not exact, not drawn to scale whatsoever. But if you look at the question, I am looking for the area between 0 and 2. So in other words, I'm looking for this area and for this area. Agreed? Yeah, see what I'm saying? So, because we know that, we also know that with absolute value, we can say that if we didn't have this as an absolute value, couldn't we say that this line right here would be the function negative 2x minus 1? Because it has a negative slope. And then we can say that this line right here is the positive 2x minus 1. That's the whole point of absolute value, right? Well, how can I use integration? Well, I know this is for this smaller area here. So if I want to find that area using integration, I can say that I can use the integral from 0 to 1/2. Yes, sir. Sure, but then you just got to apply the rules. Why not? Okay. So from 0 to 1/2 of what? Can I go ahead and distribute that in and say negative 2x plus 1? You guys okay with that? Negative 2x plus 1 dx. And that's going to give me the small triangle. Plus the area from where to where? 1/2 to 2 of 2x minus 1 dx. Cool? So now you got to solve each one and add them together. Because if you would have not recognized that and you would have gone straight from 0 to 2, just using the 2x minus 1, you would not have gotten the correct answer. You would have been missing this small little triangle here. Okay? Alright, so try it, and I'll reveal the answer here in just a second. And that's really all I got for y'all today. For homework, I just need you to complete on the sheet 5.3 and your quiz. We'll finish 5.4 next class and start 5.5. Cool?